first presentation this afternoon, is NDE and materials testing for bridge deck condition and service life assessment for asset planning. We have with us today Shane Boone, PhD, Vice President for NDE at BDI, and Michael Brown is a Senior Supervising Engineer with WSP USA and serves as the firm's U.S. Bridge Asset Management Leader.
All right, thank you, Tim, and thank you all for attending. This was a joint project, not just the specific bridge that we'll be speaking about, but also putting together this NDE asset planning using a multi-phase approach. We've kind of been going through this the last few years and really started to hone in on what kind of data we can get using non-destructive testing tools on bridge decks and how we can use that data for better asset management planning. So my co-speaker, Dr. Michael Brown with WSP, and then also InfraSense provided a lot of the data as well. Just to kind of talk about what we're going to talk about specifically, because there are two integrated presentations here. The first part, which is what I'll be speaking on, is how we use NDE tools to identify degradation in bridge decks, talk about the technology specifically that we use and the goals of the study that were applied to this specific bridge, how we used those goals and the technologies to collect the data and some of the results that we got from those. And then Dr. Brown will speak on how we use those results for the condition assessment, modeling, and life cycle analysis. And then hopefully we'll have some time for questions and discussion. Right off the bat, I mean, everyone in here is a preservation person, and you know primarily why bridge decks degrade. If it's not from a loading scenario or impact or something like that, 9 times out of 10, we're going to have degradation due to chloride ingression and subsequent corrosion of the steel. As that steel corrodes, it expands. Concrete's not very good in tension. We all know that. It cracks. We get delaminations and spalls. Luckily, we've identified which specific tools across that time frame that we can use to identify that degradation. We can use electrochemical tools like half-cell potential to identify whether or not we have a corrosion cell that's active and whether or not the rebar in the structure is going to start corroding. From there, we can use GPR, ground penetrating radar, and identify those precursors to degradation. So do we have chlorides present? Is there moisture? Do we potentially have loss of cross-section? Once we have that loss of cross-section, we can use acoustics to identify whether or not we actually have a true spall or horizontal crack. And then eventually we get to the point that we're all used to with hammer sounding and chain dragging. We can actually hear that. We can use infrared thermography to see those shallow delaminations as well. So we essentially use all of those tools to accomplish what we've always done with chain drag. So instead of closing down a lane and doing a manual chain drag that may or may not be reliable, you know, I've heard of people with golden ears, and I don't know how golden those ears are when there's a 30,000-pound truck going by them at highway speeds. It's sometimes hard to hear. You know, whether or not it's repeatable is another thing that we run into. And so we use these quantitative tools to be able to actively inspect the deck and be able to have these reliable, repeatable results. So the goals of the project itself, specifically to this deck, but also in general, were to use conventional testing once we get to that point and innovative rapid NDE of concrete decks to assess their current condition, predict the future deterioration, and support service life and life cycle cost analysis so that the bridge owners can actually use this data in their life cycle analysis and their asset management plans and so on and so forth. But we also have to be able to use this on a large scale. So whether that's on large signature bridges like the one we'll talk about, we can't talk about specifically what bridge it was, but I'll give you an idea. It was an 11,000-foot 4-lane structure, so a little shy of 600,000 square feet. We were able to do that bridge in just under 6 hours. So, you know, traditional chain drag, you wouldn't even get close. It would take you months. But then also have larger quantities of inventory. So we've recently done 137 decks across a specific state in a little under 30 days of working. So it gives us the ability to not just get one single structure in a fail swoop, but also to do these large quantities of inventory at one time. And it allows the owner to proactively plan their maintenance, their repair, preservations rather, and have repeatable quantitative data. So how do we do this? We use a phased approach like I've presented on before. Phase 0, we identify which decks we need to inspect, you know, whether that's through a typical MBIS data review, you know, age, recent maintenance, which decks need to be repaired. all the way to an aerial IR survey where we can identify, an entire corridor within a day or two. From there, we can go to a phase 1 inspection and do network level inspections using high-speed infrared GPR and HRV. We identify which of those structures we now need to really get high-resolution quantities and show our clients, what they're typically used to seeing with chain drag, so get the quantities with regards to acoustics. And then the phase 3 is where we get into the preservation portion and why we're all here. We take all that data, provide a maintenance plan, provide a plan for preservation, maybe monitoring, maybe an overlay, what have you, whatever that data tells the story of. So jumping right into it on phase 1, InfraSense provided the high-speed GPR. So these are 2 air-coupled GPR units hanging off the back of their truck here. And then on the top, we have a high-resolution video camera and an infrared camera. So we can perform this survey at high speeds, typical whatever the posted speed limit is, no invasion to traffic whatsoever, and essentially go through and get a very high-resolution video and stitched image of the bridge deck. So we can go back, instead of just doing a visual inspection where I take the picture from here, Mike takes the picture from over there, and 5 years later you can't decide what view you're looking at. We stitch those images together and we're able to identify specific quantities of patching, spalls, anything that we would want to know from a typical visual inspection. We also go through and map the GPR and the infrared images over top of those high-resolution video, so we can see areas that we're going to have potential corrosion, potential problems in the future, and also areas that we have existing delaminations caught by infrared. One thing I'll say about this deck is that it was in pretty bad shape, and Mike will get into some of that. So when I'm showing these images here in a minute of the total overlay with the infrared, the GPR, and the SoundR data, it's going to look pretty bad. So I'm just giving you fair warning there. Also with GPR, we can get the cover depths of the rebar, which Mike then can use in his diffusion models and identify, why we have these reasons for some of the corrosion that we have. And then we get into the deck acoustics response. So I'll go into this a little more detail since it's a newer technology. It's a technology we've been developing for the last 5 years or so. It's essentially a lane-wide automated chain drag. I mean, that's the best way to say it. We're using impactors instead of chains, so the easiest way is to just show a little video. So essentially what we have there are modular impactors. They're spaced a foot apart. They're going at 2 hertz, and the impacts are made at about 40 milliseconds apart from each other. So essentially we're not getting any acoustical crosstalk between channels. The impactors themselves are modular, so we can range anywhere from 6 millimeters to 25 millimeters, allowing us to get different dynamic induction into the deck. So if we want to look at a deeper deck, we have the ability to do that. And then the microphones themselves are designed to isolate noise from outside traffic, focus the acoustic energy that we're really looking for. And the reason we did that, we didn't just, reinvent the wheel. We went back and looked at what Federal Highway had done and other researchers. And acoustic and air-coupled impact echo has been a topic that has been studied in recent years. And the primary thing that everybody has found is that it's very hard to capture these little tiny, not very loud air-coupled zero-group velocity S1 modes. That's very detailed speak for the energy that we're looking for. For the most part, most of the energy that we're looking for is dominated by just the air-coupled impact noise and the leaky Rayleigh waves that travel across the surface. So we have to isolate that noise going into the microphone and make sure that we're capturing the right data. Those 2 slides in this slide are just essentially showing that we did our due diligence in developing this device. And then essentially what we did was we tried to take a step back and say, okay, well, what is impact echo? How has it been used in the past? How does it compare to chain drag? And what do the clients and the stakeholders really need to see? Because if you've ever used impact echo, you know that you can go out and you'll find maybe a small horizontal crack, and then you'll follow it up with chain drag and say, well, do I really need to repair that area or not? And so we wanted to develop a device that captured everything from impact echo all the way up to chain drag and got to what the clients are used to hearing, which is essentially the human ear hearing a chain. So it's not necessarily impact echo. It's a common misconception. We've developed a new way to analyze data, and it's essentially capturing all those things that impact echo would capture on a very high resolution basis, but also capturing the things and identifying the things that you would regularly see with chain drag. We can then use those different modular impactors to analyze at specific depths and perform a regular impact echo analysis if we want to. The issue that we ran into is obviously this is only 2 minutes worth of data from one channel. So you can see that if we went across a 10,000 foot structure, it takes about 45 minutes. We've got millions of data points to analyze. Not only that, but even though we've isolated the noise quite well, we still run into areas where you can see heavy traffic noise, and how do we get rid of that, because that low frequency flexural dynamic is what we're really looking for. That's what the human ear hears. So first thing we did was we did some just standard Butterworth filters, removed as much of the traffic noise as we could, got a nice clean signal. And then we started seeing, okay, well, what is indicative of what we would hear, and how does that compare to impact echo, and how can we capture both? So you can very clearly see here's a single impact by one of the impactors. The sister impacts from the 2 channels beside it, you see that we've got enough time between them to essentially allow that noise to decay and not get any acoustic crosstalk. And then you can see areas that are structurally sound on both sides and areas that are degraded. And how do we know this is degraded? Well, on structures for years as part of the Sharp 2 project, we went out and chain dragged and hammer sounded and did cores and chloride samples and infrared and GPR and validated that data. So we didn't just say, okay, well, that's an area of high frequency noise, so we're going to call it delaminated. The best way, again, is to just kind of show you what I'm talking about here. So essentially, here's the same about 20 seconds worth of data. Here's the region of that low frequency noise that we were just looking at. So again, this would be an area that didn't show any of this black low flexural noise, and these areas would be ones that would. So if you look and see this little black dot here, each one of these green dots is one of the channels as it rolls across the deck. The black dot is indicative of what's coming from this specific channel. And so I'll go ahead and play that, and you can see as we get to these specific areas, that's how we identify areas of degradation. See how it works? So we've essentially created a system that mimics chain drag. We use that system to follow up with our GPR and infrared and HRV systems to identify how we can truly capture all the degradation information from the bridge deck. And then essentially we've automated a system that can analyze thousands of impacts very quickly. We perform a cluster analysis, and that result essentially mimics what we get with traditional sounding and impact echo combined. So now I'm going to show you the picture that's scary. This is what the bridge deck looked like, a few segments of it. So you can see all the little red spots, right? That was from the infrared. The SoundR captures all that. But then we've also got these areas over here where SoundR captures it and infrared doesn't, and GPR captures it as well. What we're seeing there are the areas that impact echo would capture a very small horizontal crack, might be on the bottom section of the deck, on the bottom mat of rebar, and the GPR is capturing corrosion that it's occurring. It's just not a big enough delamination to be captured by infrared. So we're able to capture all of that information. And then once we get there, Dr. Brown will talk about what we do with the data.
So thanks, Shane. So in the example project that we're discussing here, we did all of that sort of data collection, and then in this case, clearly we had situations that needed attention, so we were doing a more detailed assessment. So we complemented the rapid NDE work with conventional sampling plan. So we did core sampling along the length of this bridge. And you can see the bridge is 4 lanes wide. It's multiple spans, some approach spans, some suspended spans. And altogether, there are 416 distinct segments in this bridge if you take the number of lanes times the number of spans. So we took the cores. From that information, we got a lot of the conventional types of outputs we would do in an assessment. We're looking at the compressive strength and the modulus to understand the structural quality of the concrete. We did petrographic analysis to screen for the overall quality of the materials, understand some of the parameters of the concrete, what's the approximate water-cement ratio, what kind of an air entrainment system do we have in place. More importantly, do we have any indications of other forms of degradation besides chloride ingress that might contribute to deterioration? So we want to screen for those things because if they exist, of course, our strategy would be adjusted accordingly. In addition, we measure the pH and the carbonation. So for example, here on the right, you can see where we've done the phenolphthalein test on an exposed section of the core as part of the petrographic analysis, so we can understand depth of carbonation. Then we do the profile sampling. So we take and subdivide our core into increments. In this case, we use half-inch increments that are strategically layered to understand the chloride ingress, and then we plot, after we test for the chloride concentrations, we plot those into the profile in the lower right corner. And so that gives us an understanding of the chloride distribution into the concrete from the surface in the area where the cores were taken. From that, we can apply model to understand essentially what is the chloride loading at the surface based on the de-icing operations, because that's the driver in the environment where this bridge is, and also the effective rate of diffusion of the chloride over time. As Shane mentioned, we also have the ability from the ground penetrating radar to get very detailed information about the cover depths, the cover depth distribution across the structure, so we get a nice statistical representation of clear cover. Clear cover is an important input for our diffusion modeling, and so that helps us understand which percentage, the shallowest percentage of the bars are most likely to corrode first as the structure ages. In this bridge, again, I said there were 416 different segments, and this bridge has been in service for several decades and has actually gone through a considerable amount of rehabilitation. So the color scheme here actually shows by function of age of the overlay. They've gone in these individual segments and individually overlaid segments as they deemed it necessary based on the observed deterioration. So the red color are actually the older overlays, and then moving towards yellow and then green for the more recent overlays over time. The white boxes are actually segments that have never been overlaid. They're still original deck. So this had quite a variety of behaviors given the time frame that it had been in service. And so in essence, we had to treat all 416 segments as if they were each an individual deck to do our analysis. So using the inputs that we got from our concrete testing with the chloride profiles and the cover depth distributions that we got, using target concentration of chloride that we expect to induce corrosion, then we can plug into a model, and we use a method called Monte Carlo simulation to run repetitions of the model to essentially calculate the time that's expected for corrosion to occur based on the chloride exposure, the cover depths, et cetera, and then we can put that into a service life projection. We did that and essentially came up with values for each of the segments that we're looking at. We then took the NDE data. So the first variable here, SL, is essentially the service life prediction based on the model I just discussed. The second one is essentially GPR. Third is infrared. The fourth is the deck acoustic response. And then finally, the high-resolution video. So each of those is normalized as a percentage area of the bridge deck. for a given segment. And so we've got those values all essentially as a function with the same basic parameter, deck area, and come up with a customized index, if you will, of condition. To those, we apply a weighting for each one depending on what we're trying to analyze. So this, what I call a utility function, was applied in one case to assess what is the overall current condition, and then also to assess what is our expected future condition, predicted future condition. So for near term or the present condition, we were able to essentially project for the client what are the expected near-term repairs based with heavier weighting on the deck acoustic response in the infrared as well as the high-resolution video. Keeping in mind the high-resolution video also allows you to assess existing patches and cracking. So that gives you some additional information. So that is the heavily weighted portions for the index to come up with what are our near-term needs. For the longer-term needs, we turn more towards both the service life prediction and also the output of the ground-penetrating radar, because the GPR actually, with the attenuation of the signal, you can interpret that and get indications of what we call precursors to corrosion. So areas where you have high levels of moisture, areas where you have high levels of chloride concentration will actually serve to attenuate the signal in a way that it differentiates from the other areas of the deck. So those, in that case, for the longer term projection, those things were weighted more heavily. Then we just apply traditional life cycle cost analysis to the outputs to look at different options for addressing either the near term or the long term needs, depending on what the client's goals are in terms of preservation of the structure. And then you can, as you would with most rehabilitation projects, look at your various options depending on the degree of damage that you're seeing, the severity, and the breadth of the damage, the different types of techniques, and also specifically the timing of when it would be ideal to do those to get the best life cycle results. So we essentially did that with this structure and came up with a projection. They were specifically interested in understanding whether or not, given the extensive amount of overlaying they had already done over the years, whether or not they really need to just go ahead and replace this deck now, or if there are options to effectively extend the service life of the deck. And so we looked at that with questions of timing and also cost to try to give them the best idea. The result being, of course, an analysis of the options, looking at a uniform analysis period, summing up essentially the results for comparison in present day dollars, and then at their option we can include or omit user costs if that's important to them. And that gives them some well-reasoned information upon which they can act in terms of making their preservation decisions. So circling back to where we started, where Shane went through the goals for this project, we just want to kind of close the loop and show. So our questions were, okay, the idea is we want to use both the conventional testing, the innovative NDE, to assess the current condition. Yes, we did that. The current condition, which was heavily supported by the soundar, the infrared, and the high-resolution video. We also did the future predicted deterioration, heavily weighted by the GPR and the conventional testing and service life modeling. And we were able to provide support for decision-making related to service life and life cycle cost analysis. Shane had mentioned this has been effectively used in this case for a very large signature bridge to make rapid assessment of just how severe the condition is and what the owner can expect. As he also mentioned, we've teamed up to look at a series of much smaller bridges, but over a very short time frame is more of a screening and prioritization tool. And then from those, you could individually decide which ones need more immediate attention and do the more traditional service life and planning approach, whereas those that don't indicate imminent problems, you have that information and you can come back at a later time and essentially resurvey and see what the progression of the deterioration is over time just based on the rapid NDE results. It's a very efficient way to track the progress of deterioration in your inventory. And so then all of that comes together to support service life planning and a way to manage your assets. I guess we can open it to any questions.
How was the instrumentation able to differentiate between transverse and longitudinal, both upper and lower bars?
Well, on GPR, we only capture the transverse bars because we're traveling across them. If we wanted to get the longitudinal bars, we'd have to do a scan across them. GPRs typically are only unidirectional in their antenna focusing technique. So for the high-speed stuff, unless we go back and do a ground-coupled system, we only get the transverse bars.
And are you able to capture both lower and upper, or how are you able to differentiate between the two?
Yeah, so the frequency, I should have put a plot in there of what we're actually capturing. The frequency of the antenna, Adam, correct me, is 1.6? 2 gigahertz, so it's a 2 gigahertz horn. So it's good to look through about 12 to 18 inches. So we're able to capture both the top and bottom map.
I noticed in your video that was a very textured surface. How do you account for that on that acoustic kind of rebounding technique to account for that?
You're talking about like the timing in the concrete?
Well, the timing of the pings, does it disturb or create a bias in the data that you would have to be able to account for? Because you're not going to, you might hit on a peak, you might hit in a valley.
Well, for the most part, the spheres that we typically use are about an inch in diameter. So as long as there's not a huge dent or a spall, it's not really an issue. And then if there is a spall, it would show up in the high resolution video, and so we captured in both things. That's one of the reasons we do high resolution video with the infrared, and it also accounts on the deck acoustics. But for instance, if there's a puddle there, you want to know that visually it's a puddle. It's not just a cold portion of your deck.
So I'm just curious, what was the outcome? Was it you're going to replace the deck, or was it you're going to go in and do repairs?
Actually, we're working further with this client, and we're evaluating a comprehensive overlay using some more robust approaches than what they've done in the past. In the past, they've done simple milling and latex shallow over the top mat, and they've had very limited success with that. They get an average life of maybe 10 years out of those, which is why you see so many. Some of those had actually been overlaid more than once. I didn't really point that out. Now what we're looking at is a deeper overlay using a deep hydro to capture the top mat, and potentially using UHPC. Right now we're comparing some of the rapid latex overlays to UHPC as potential options, because the UHPC is so impermeable compared to our conventional concretes that you're not going to have a big issue with chloride ingress in the future. And the UHPC adds some strength so that you would actually have a pretty robust structural rehabilitation of the deck if you're able to get below the top mat and incorporate that. So we're looking at that now. We're actually going to do some comparative options, a demo, if you will, in the field to try to see how those play out.
As a bridge inspector, I'll go out there and I'll see decks, and I can visually look at them and tell pretty quickly that this deck's got problems. And based off of the scans that I saw there, I don't know if I saw a picture of the deck, but this looks like one of those cases to me where you'd be able to walk out there without doing all this testing and determine that.
Well, yeah, except there were areas of the deck that were really sound, and there were areas of the deck that had significant rehab or some patching. So the thing is, I think we're looking at an option where we can do a significant overlay, which will be expensive, but it's nowhere near as expensive as deck replacement and nowhere near as disruptive. And we're looking at potentially being able to push off deck replacement for 20 years or more. This could be very cost effective, and understanding what's underlying that whole deterioration process and making some intelligent decisions about that can help you in terms of better asset management, other than just throwing in the towel and saying, let's just replace the deck.
Yeah. A follow-up response, Mike, is that you're correct. I mean, I actually walked this bridge as part of the deck acoustic inspection, and you could hear it. I mean, it was in some places just torn all the bits, but the client always has so much money, so they have to be able to make a hierarchy of which areas they are going to repair first, and that's where that data comes into play.
I didn't mention, but we were also doing follow-on to some work that was done about 8 years ago, and they wanted to actually compare results today to what they had measured 8 years ago to understand the progression as well. So that was a piece of the puzzle.
Thank you.
Thanks, guys.
Do we stay up here, Sam, or do we leave? I'm gonna.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.